So here goes. This is the result of a thesis of a student of mine, Luis Gomez Ardila. I'm letting everybody in, okay? I hope no one is complaining. And it's a very interesting problem, very, very interesting problem. Actually, let me tell you a bit of the story of this problem. McKean-Scovel was a student at the Current, and he started under the supervision of Henry McKean, which is one of the coolest, right? So they started considering the simplest nonlinear Tomei view operator. And everybody is being invited. I want to invite everybody, okay? So at some point, there was a very natural question about how complicated was really the map associated with this nonlinear Sturm view operator. And McKean wrote a paper on the Journal of Differential Equations where he gave his opinion on the matter. And beautiful idea. Unfortunately, there was a fundamental mistake in his argument, which was identified by Bernard Ruff a few years later. And the problem stayed in the air. We're talking in the late 80s. And it's been years I've been thinking about this problem. I have the occasional partial success, okay? And finally, I think I have a story to tell you. I will not be able to provide complete details here, but I hope there's a sufficiently clear map for you people to see what the problem is all about. Okay, so here's the map. Okay, you pick a function with two derivatives, Dirichlet boundary conditions, and perform this computation. Big deal. And now let me tell you a very interesting fact about this map. You give me any number, you give me any epsilon, and I'll find a right-hand side for which this equation has n solutions which are epsilon apart. In other words, I can find arbitrary large clusters of solutions for specific right-hand sides, okay? How do you go about proving something like that? And indeed, this is a consequence of this fact here. If you consider this function f over here, and you consider its critical set, the critical set will contain arbitrarily deep Morin singularities. And of course, the fundamental question is, whoops, Morin singularities. So that's the whole point, okay? I want to spend some time with you guys to try to convince you that this is beautiful technique, very powerful technique, actually. I'll start slowly, okay? So first of all, I guess we all know what a critical point is, right? You consider the Jacobian of the McKean-Scovel operator at a point U, easy computation. Notice the appropriate notation here. And you look for points U for which this map here is not invertible. There's an amazing lucky break here due to the fact that this is a Dirichlet problem. And we know that the kernel of such operator is at most one-dimensional. More than that, it's a Fredholm operator, index 0. The gods are on our favor. Now, it turns out that a critical point is very easy to describe. Well, let me be more precise. We all learned about the inverse function theorem. It says that if at a point where the Jacobian is invertible, your function is a local diffeomorphism, okay? Turns out that most of the points when this doesn't happen are still very easy to talk about the function in that neighborhood. We're talking about folds. After changes of variables, which are local, both on domains and counter domain, your function becomes essentially a parabola. You see, x goes to x squared, and you have to fill up the remaining dimensions of your ambient space, okay, with a variable on which nothing happens. It is like a large Lyapunov-Schmidt factorization, okay? The bifurcation equation is extremely simple, okay? The word fold is more than appropriate. And if I were giving a live lecture, right, I would insist on the fact that functions are just nonlinear origamis, right? You have a piece of rubber here, right? Your domain is just a sheet of rubber. And now what a global fold does is you take this rubber here and fold it, okay? Oh, whoops. But it's terrible. It doesn't work through Zoom. Well, it turns out that not every critical point is a fold, okay? The next in line, oh, I should have mentioned the fact that this is the very soul of the Ambrosetti-Prodi theorem, right? They realized that every critical point of the Ambrosetti-Prodi operator was actually a fold, and they were able to convert a local statement into a global statement, okay? The differential operator related to the Ambrosetti-Prodi context is really a global fold. The next in line is a critical point, which is a cusp, okay? And it's slightly more complicated. Again, there's lots of padding, okay? And action is really going on in two variables, okay? And it goes like that, okay? Turns out that this is already an interesting animal in many senses. For example, just to give you an idea, forget about the z variable, and what this function from the plane to the plane does is the following. The critical set is a parabola, which is sent to this strange object here. All computations may be performed explicitly, but the interesting thing is the following. This vertical line here goes diffeomorphically to this line here. This vertical line here goes homeomorphically here in the sense that actually it stops here. The behavior of this function along this green line is actually y goes to y cubed, okay? Still homeomorphism. The amazing thing is what happens when you look at a line on this side here, because now x is negative, and your function actually, whoops, covers each point within this region 3 times. So you see, this is a very concrete way of identifying points for which there are 3 preimages for a certain map. And actually, this was the technique that Marta Kalanki and I used to show that if you have all the hypotheses of the Ambrosetti-Prodi theorem, but decide that F is a non-convex linearity, then necessarily some right-hand side has 4 preimages. Okay, that was one of the first steps which were required to try this more ambitious problem I'm trying to show you today. Okay, let's push further. Now I have to introduce some notation which is all rather familiar. Think that the Jacobian, which depends on the point on the domain you're operating, okay, induces a collection of simple eigenvalues. We're talking again about the U-shaped problems, okay, which are going to be dependent on U, and there will be related eigenvectors, okay? And you check what you're supposed to do, and it turns out that all such maps here are really smooth maps with respect to this variable U, okay? Keep in mind that what I mean by smoothness is Fréchet smoothness, okay? Because we want to use results of the kind of implicit function theorem, okay? So Gateau type derivatives, just like people in mathematical physics use, wouldn't be sufficient to what I want to do. And now let me define a collection of functionals, okay? The first one is going to be just the eigenvalue at a point. Of course, there are so many eigenvalues I have to index. N is going to be fixed for each U, there's going to be a specific N. And this is my first functional of interest. Okay, and then what I do is I start taking partial derivatives of the eigenvalue with respect to the associated eigenvector, which is something people in mathematical physics wouldn't do. There's no real reason. I couldn't find any real reason for this computation. For geometers, however, this is an absolutely natural question, okay? Essentially what you're saying is that, say you have an eigenvalue equal to 0, eigenfunction is of course a direction in which your function is going to misbehave, right? And actually you want to check the order of misbehavior along that line. So the definition of a Morin singularity is that you have a billion of directional derivatives equal to 0 until a moment when it's not 0. Okay? 0 index k minus 0 index k plus 1. And of course, I guess you expected this one. You need transversality, right? You want all such gradients, for example, to be linearly independent. Okay? This ensures the very convenient fact that all such sets here, at least locally at a point U, are manifolds. Okay? And this is a fundamental result of Morin, and people like Barboni Donati, Jim Damon. There was a version of that in a paper with Yassi Malta and Nicolau Saldanha, also tried to convert Morin's results into an infinite dimensional statement. It essentially boils down to the fact that there is a Malgrange preparation theorem on parameters which are in Banach spaces. So what I want to tell you is the following. Again, there's a padding variable here, okay? There's a very special direction, t, in which your function looks like t to the k plus 1. And those guys here are actually indicators of a very interesting property. Those are all possible perturbations of this fundamental map here. This is what transversality gives to you. So what this is saying is the following. There's a special line, actually a special curve in the domain on which your original function f is going to look like t to the k. In other words, t to the k plus 1, I'm sorry. In other words, there are lots of roots sitting one on top of the other at the point 0. Better still, if you just do the right perturbation, those roots, they open up in all possible ways. Well, you know what the trouble is when you do perturbations over the reals, right? Sometimes things go complex, you lose roots, okay? Sometimes, on the contrary, you will be able indeed to find all the roots you started with. And this is the case when you're sitting on top of a Morin singularity. Morin is a key word here, okay? He was the guy who realized that if your derivative is not really that nasty, if there's only one direction at most in which you are losing invertibility of the Jacobian, things are absolutely operational, okay? The local behavior of a functional, of your original function is given by this formula here. Amazing, amazing, very crystal clear. Okay, so this is what I wanted to show you about what a Morin singularity is, and actually, you immediately get this result, agree? There's going to be a right-hand side for which you're going to have the appropriate cluster being undone into a bunch of isolated ray images. It's really that simple. Very convenient. Of course, this is very geometric. This is essentially a fundamental definition of what a Morin singularity is, but we have to bring it closer to the McKean-Scovel operator. So the first remark is the following. Belonging to Z1, which is the use for which one eigenvalue equals to 0, is essentially stating that you have an eigenfunction, which I call U1, and its eigenfunction is associated to an eigenvalue equal to 0. Okay? Next. This means the following, that there's going to be a solution. You see, how do you go from this differential equation to this one? You just take a partial derivative with respect to U1, okay? So I denote the derivative of U1 along that direction by U2. There's a product rule. A term goes here. The other term is minus U1 squared. Now, the existence of a solution to this equation here with Dirichlet boundary conditions is a standard fact, right? The right-hand side ought to be orthogonal to the kernel of the self-adjoint operator. Okay, so this is an epsilon more concrete description of a functional which specifies when a function U belongs to Z2, okay? Keep in mind that in order for you to have a Morin singularity, there are two kinds of hypotheses. One of them are of a more algebraic nature. Something has to be zero, okay? And others are transversality statements. Certain objects have to be dependent or have to be non-zero, okay? Now we're concentrating on the algebraic part of the story. Again, if you take this derivative here, you get minus U3, product rule, one term goes here, another term goes here, more derivatives here, ta-da, you get this guy here. And the next functional you have to live with is this one here. Okay, more generally, okay, if you start taking derivatives, you're going to have to solve equations of this form here, where the right-hand side is a bilinear expression in the previous solutions of your system. Okay, and once again, the usual functional analysis trick, right? Linear algebra trick, let's be honest, right? If you want to have solutions, you must have that the inner product of the right-hand side with the kernel of the operator on the left-hand side should be zero. Okay. Well, let's be honest, this is a mess. And it turns out that at this point, I don't really know if this is that complicated or we're missing something. For example, a fundamental property of this nonlinear system is the following. I rewrote the system here, okay? The RJs are defined as before, and I insist that you're solving an initial value problem. Your function is zero on the left, and the very first derivative is different from zero. It turns out that there's a very special linear combination of those solutions here for which we are still solving the same system, but now you reduce the boundary conditions to an almost canonical form. You see, that's a little algebraic miracle because this system is highly nonlinear, okay? Is this important? I still don't know, but the fact is that I cannot live without it at this point. Okay, transversality is delicate, but to be honest with you, it's feasible in a sense that we perform a lot of calculations. It turns out that the calculation was originally inspired by computer work, and I'll tell you more later about it. So this very first remark here states that if you indeed have solved all the algebraic issues you had to solve, then the independence of the gradients is automatic, okay? This you perform by checking the asymptotic behavior of the many solutions of the system at the origin, okay? More than that, you can also prove that if you have a critical point, you cannot have all possible directional derivatives along the eigenvector equal to zero. This is not possible. And this is essentially a slick analyticity argument, okay, the usual business. If a certain function, but actually the function in question here is the eigenvalue itself. If a function has all its eigenvalues, all its derivatives at one point equal to zero, okay, then along that line with direction vector given by the eigenvector, okay, this function has to be zero, okay, and we derive a paradox out of that, okay. So for all intents and purposes, if you're interested in that, you should go through lengthy, delicate arguments in the text with Luis. Okay, and here comes a very convenient trick, which actually was used in previous, how should I put it, exercises related to contractibility arguments with Bulgaria, Mountain Saldanha, and again with the non-convexity implies non-Ambrosetti Prodi with Marta. The idea is that instead of thinking your potentials as being H2 functions, which are, well, very non-flexible functions, right? If you want to do any kind of construction, you have to make sure you are in H2. What we do is we replace such animals by sums of deltas, which are essentially functions in h to the minus 1. And just for you to have an idea of what that means, suppose you're talking about, again, that the original nonlinear problem, okay, in the interval minus 1, 1, and my potential is going to be minus 2 delta at the point 0. So the potential is 0 over here, it's 0 over here. The eigenfunction has to start linear, okay, starting from 0. It has to be linear over here. And this minus 2 here is exactly what it takes to make sure that you have the right bending here, okay? So again, this inclination here, the slope is 1, this slope is minus 1, this minus 2 was forced to me, okay? So there's a typical potential U tilde for which you do have an eigenfunction. Well, let me be very careful at this point. I'm not extending the McKean-Scovel operator to h to the minus 1, because remember, you have to square the potential, and I don't want to go radioactive on those issues. What I'm doing is the following. I'm looking for a Morin singularity. That means solving a certain system of equations, okay? And it turns out that it is the potentials occurring on that system which are going to be extended. To be honest with you guys, you almost will not notice there are deltas in town, because once you solve the differential equations, you get what you see. Where's the delta, okay? You start working with functions which have the occasional hiccup at a few points, okay? Of course, we'll have to somehow get back to the real world, right? Once we are able to solve the algebraic system of K equations in this larger space, then we'll have to do some kind of smoothing. This other example actually is a cusp, okay? U now has a delta over here, another delta over here, and you just point, bounce, okay? Well, it turns out that there's an amazing lucky break here. It turns out that because your eigenfunction is 0 over here, you might as well add any multiple of delta here, and this would still be a solution to you to belonging to Z2 system. In other words, actually, this guy here belongs to a line of cusps, not only the one which contains those two deltas here, but you can add an arbitrary multiple of delta over this point here. And this is going to be a really important thing in our argument. Now, as I was telling you, of course, what you must do is make sure that once you enlarge the space, you don't lose your animals, right? So eigenvalues still make sense, eigenfunctions still make sense, the functionals which characterize the Morin singularities still make sense. And again, this is not such a cheap business, because essentially what I'm doing is Fréchet's spectral theory on h to the minus 1, okay? It's feasible, you just breathe and do it. So this is exactly what I claim, okay? You're going to hunt for a solution of the same system as before, very nonlinear system, and now you cross fingers, okay? Let me be honest, crossing finger means you go to the computer, you have to find some intuition somewhere, okay? If you don't get an intuition, you get at least some conviction that McKean was right at this point, we are close to the edge. What if it's wrong? So, and it turns out that you can perform all kinds of natural operations and you're still in good shape in the following sense. You shouldn't be surprised if I told you that if you pick one eigenfunction and you juxtapose it to another eigenfunction, okay, provided you do the right gluing here so that, well, if you are in H2, right, you need some information about the derivative. So provided you have the appropriate gluing, you're going to find an eigenfunction to a larger interval, okay? It turns out that that works also if instead of talking about the critical point, you're talking about a Morin singularity of order k. Juxtapositions of two Morin singularities of order k yields another. It's not a trivial fact. Okay, to say the very least, you have to have a very operational description of what the Morin singularity is. Okay. More than that, of course, you may be thinking that once you do juxtaposition, your original interval 0, 1 becomes 0, 2. But that's what I mean by saying that if you perform scaling, Morin singularities preserve their depth. That's easy. So scaling, translation of the interval, and reflection. Reflection is just this. You have a certain potential here, you, whoops, flip it. Okay, this also preserves not only criticality, but Morin depth. Juxtaposition is the kind of animal I was describing before. Symmetrization is, well, is something very natural. You start, say, with an eigenfunction, you reflect it, now you try to juxtapose, but of course, the moment you juxtapose them, you have to make a correction here in order that the derivatives fit well, okay? This whole process here, we call symmetrization, and this is one of the real lucky breaks in this whole story. For example, if you start with an eigenfunction here, okay, this process here will obtain a cusp for you. In other words, you might have started with a fold, which is a Morin singularity of depth 1, and now you have a Morin singularity of depth, oops, sorry. Those numbers are wrong. Okay, it should be 2k minus 1 to 2k, I guess. Okay. So what I'm saying is the following. If you want to get larger and deeper singularities, okay, you might think that you start with a simple singularity and you start performing operations on it in such a way that you get deeper singularities. Well, you can go, for example, from a fold to a cusp, okay, which should be even to odd, which is just the opposite of what I wrote here. Still, we are left with the other case, okay, which is, of course, not written well here, okay? And this was very hard. We really have to give a lot of thought to this problem. And I'll give you a flavor of how we handle this. Let's get used to the notation. This is a fold, okay? Fold has depth 1, and there's a single delta, remember? Here, there's a single delta of weight -2 smack in the center of the interval, which is what this notation is saying. There's a single delta centered in the center. So let me just put the minus sign over outside, okay? Now, what this is doing is symmetrizing the problem, and I'm adding the degree of freedom I was entitled to incorporate at the origin. Let me get back here. -2, and an additional degree of freedom over here. okay? So for any value of A here, this collection of 3 deltas is associated to a cusp, okay, a singularity of depth 2. When k equals 3, you do the following. First, you symmetrize. You see that these first 3 guys here have to do with those 3 guys here. The last 3 guys have to do with those 3 guys here. But keep in mind, the moment you symmetrize, this number here doesn't have necessarily to be equal to this one. Okay, so now you have a plane of cusps. As an extra bonus, you get the additional degree of freedom at the origin when you perform symmetrization. Okay, so at this point here, what I'm telling you is the following. If you want to look for the next singularity beyond cusp, which is swallowtail, okay, now you have 3 degrees of freedom to play with. Okay. Remember that in principle, this guy here is solving the first 2 equations. Okay, this guy here automatically solves the first 2 equations, okay, to be in Z1 and Z2, and you have 3 degrees of freedom to solve for the 3rd degree of freedom. If you perform yet another step, those guys here are copied over here. Those guys here are symmetrized over here. You get an extra degree of freedom here. And you see, you have, wow, 1, 2, 3, 4, 5, 6, 7 degrees of freedom to solve for the 2 equations I didn't solve before. Okay. Of course, this is very hopeful, right? What this is saying is that it's just a matter of choosing the right values of parameters throughout the place, okay, in order to get something fair. And indeed, let me show you how we did it. Just like before. Now, whenever I copy this to the left, I simply forget all degrees of freedom I had. So I added this 0 here. This guy is the central degree of freedom, which was added. I keep it, okay? And this guy here goes symmetrized to the other side. And indeed, I use this degree of freedom here in order to ensure that this collection of 7 deltas belongs to Z3, okay? I still have a degree of freedom here, okay? Now, I copy faithfully this guy here. I add the central degree of freedom. I symmetrize this animal here, and this guy, which was still available, I merely disregard. Okay. It turns out, as you should keep in mind, right, there's nothing to check here in the sense that, remember, when you go from a certain singularity to another of a different parity, you just have it automatically. So what I'm trying to convey is the idea that you repeat this process, you get an extra degree of freedom D over here, this C gets copied over here, and you use this guy here, okay, to ensure that now this collection here of 31 deltas belongs to Z5. I'm not sure you guys have heard of CRISPR, one of the great ideas in biology in the last 10 years, right? Spectacular, right? You have a long string of DNA, and now people manage to make a small change in one basis of this long string, right? And I catch resist thinking that this is what we're doing, okay? We have those potentials, okay? And then you have to do CRISPR exactly at that position, okay? If you want details about which position this is, which equation you're solving, of course, you have to go to Luis's thesis, okay? You see, didn't write the paper because we're trying to generalize it. Well, this is the good news. And actually, we ran this on a computer, and it worked until we weren't able to, we waited for 3 hours for the case k equals 11, and then we gave up. okay? So at this point, we almost solved the original problem, but what now, right? But it turns out actually that once we get this pattern, whenever you have to solve for a new degree of freedom, you're really solving a linear equation of the form AX equals B, the simplest possible equation. So the only difficulty is to make sure that the X coefficient is non-zero, okay? And this is exactly what may go wrong. But it turns out that there is a perturbation argument which says that, well, if you're in that context and you proved already all the transversality you wanted, you can fudge a little bit your equation in such a way that that A is not zero anymore. So this is how we get away with murder, and we are sure that we can obtain arbitrarily deep potentials given by sums of deltas. Okay, transversality saves the day. Okay, now we need to solve an extra problem, right? Remember, what are we talking? We're looking for a U in H2 space, which would be a de Morin singularity. What I gave you was a tilde U, which is a sum of deltas, which indeed belongs to Z to the K, okay? But how do you go from this sum of deltas to a function in U to H2? And this is yet another trick that has been used extensively in the papers I presented before. Pick a Banach space, a dense subspace, a C1 submersion at a point x0, okay? Pretty much, I mean, we're very close, we're hitting the implicit function theorem, I mean, even better, the local form of a submersion setup, right? So it turns out that you can find solutions to this equation here, which belong to the dense space, and they are arbitrarily close to the point you started. So you don't have to do any effort. It's really geometric. Just to give you an idea, suppose you are in R3, okay, and you're talking about a function which corresponds to two equations, okay? So by transversality, the level at x0 of this function is really a codimension 2 curve. And again, by transversality, I can draw a transversal plane to this curve here. Okay, in the sense that this plane here doesn't contain any vector to the tangent space of the level at x0. Well, once you have this plane, okay, take vertices of a simplex in such a way that x0 is interior to the simplex. And consider small balls around those three vertices sufficiently close that if you choose any 3 points here, the plane generated by those 3 points is still transversal to the red curve. Absolutely feasible, right? So what's the trick? Within that ball, you choose points in the dense space D. And now the whole plane generated by those 3 points is going to be in D. Said differently, a small plane of dimension 2 in D necessarily has to intercept this level here. This is simple degree theory once you have transversality. And this is exactly what I said, okay? You have another point in the same level of F x0 belongs to, okay? But now the guy you obtain is in the very special plane, okay? So it's a very practical smoothing trick, okay? Ideas like that have been going around in all possible generalities, especially among people in infinite topology in infinite dimensions, okay? We presented here an example, a description which was extremely simple to use and to prove. And once you have this, of course, you're done. We finally proved that the original operator has all kinds of Morin singularities. More than that, you can choose if your Morin singularities are polynomial, functions of complex support, you name it, okay? They're all there. Thank you.